global data center industry has entered a $3 trillion capital supercycle. This spending is driven by a transition in artificial intelligence workloads. We are moving from episodic model training to sustained, continuous AI inference, where every user interaction requires constant computation. This chart plots the trajectory of global data center power demand, maintaining a 14% compound annual growth rate. By 2030, capacity requirements will hit 200 gigawatts. Compare that to this flatter line of actual grid capacity. The gap demonstrates a structural deficit. In primary global markets, grid connection wait times have extended to between 4 and 8 years. Consequently, fully built data center developments are increasingly sitting idle, stranded without guaranteed power to turn on the servers. Electricity procurement is no longer a standard operational expense. It operates as a hard physical limit on the ability to scale artificial intelligence on Earth. Bypassing this gridlock requires migrating compute off-planet. Moving into orbit provides access to unattenuated solar flux and a zero-water thermal sink. This migration forces a severe industrial pivot. The primary engineering bottleneck shifts away from power generation and directly into thermal rejection. The baseline hardware remains identical. Standard commercial AI accelerators, like these GPUs, must now be adapted to operate in a vacuum. While orbit offers vast energy resources, surviving there demands a total first principles redesign of data center physics. Low Earth orbit provides distinct power generation advantages. Satellites placed in sun-synchronous orbits maintain near-continuous exposure to sunlight. This geometry enables gigawatt-scale power generation with efficiencies that are physically impassable under Earth's atmosphere. The engineering calculus changes for lunar surface operations, specifically for edge computing nodes targeting permanently shadowed craters for resource extraction. A lunar night lasts 14 Earth days. During this period, solar arrays become useless, and the mass required for battery storage to survive the darkness exceeds viable payload limits. Deep space deployments require nuclear density, specifically dynamic radioisotope power systems or fission reactors. These systems rely on the natural isotopic decay of plutonium-238. This process provides a constant, reliable baseload of thermal and electrical power, entirely eliminating the need for heavy battery banks. The deployment environment strictly dictates the power architecture. Low Earth orbit relies on the continuous geometry of sunlight, while deep space requires the continuous decay of nuclear material. Once powered, the hardware must be cooled. Without atmospheric air, convective cooling, the mechanism driving terrestrial HVAC systems, is physically impossible. This animation visualizes the Stefan-Boltzmann law. It dictates that in a vacuum, waste heat can only be rejected through thermal radiation, converting thermal energy into infrared light. Looking closely at the processor board, high-performance AI chips create massive localized thermal loads. If this heat is not captured at the source, it will rapidly melt the surrounding ancillary components. The primary conduction solution is liquid immersion. The entire motherboard is submerged in a thermally conductive fluid, like specialized oil or wax, absorbing the heat evenly across every component. High-speed, oil-free turbocompressors then pump this heated liquid away from the core payload, pushing it outward into large, deployable radiator panels that emit the infrared waves into space. Cooling in space abandons facility-wide air conditioning in favor of active fluid dynamics at the exact level of the compute module. Those deployable radiators require specialized exterior coatings to maximize their cooling efficiency in a vacuum. The standard material solution is an aluminized polyamide film, commercially known as Kapton, coated with silicon oxide. By altering the microscopic thickness of this silicon oxide layer, engineers can precisely tune the absorptance and emittance of the radiator, maximizing heat rejection into the 3 Kelvin background temperature of deep space. Thermal constraints are matched by extreme environmental hazards. Total ionizing dose radiation systematically destroys commercial off-the-shelf hardware over time. The orbital environment also triggers single-event effects. High-energy cosmic rays strike the silicon, causing bit flips that corrupt vital data or trigger systemic crashes. This diagram shows a cross-section of a protective chassis panel, utilizing a passive mitigation technique developed by NASA Langley, known as Z-shielding. By layering high atomic number metals like tantalum or tungsten over low-density aluminum, Incoming particle waves strike the dense outer layer and scatter before reaching the inner boundary, all without exceeding strict payload mass limits. Advanced materials science provides the specific physical bridge allowing standard terrestrial AI hardware to survive the harsh orbital environment. This ledger compares the capital expenditure between the two domains. Terrestrial facilities cost $10 to $15 million per megawatt to build. Orbital setups demand $50 to $100 million per megawatt. Looking at operational expenditure, the metrics invert. Terrestrial power costs are rising rapidly. Orbital OpEx approaches zero, dropping to roughly half a cent per kilowatt-hour because the solar power is unattenuated and cooling requires zero water. The financial model must also account for hardware lifespan. Terrestrial facilities operate for 15 to 20 years. Radiation degradation limits orbital hardware to a rigid 5-year replacement cycle. Investing in orbital compute requires embracing an extreme CapEx to OpEx inversion. The model trades immense upfront launch and hardware costs for operational overhead that approaches zero at scale. To make this model market viable, the industry must cross a strict economic threshold. Heavy lift launch costs must drop from the current $1,500 per kilogram down to a range of $10 to $50 per kilogram. Next-generation reusable heavy lift vehicles achieve this by distributing launch costs across dozens of flights, forcing the per-kilogram price down to the level required for financial break-even parity. If launch costs fall as projected, the industry will transition toward a hybrid architecture. Terrestrial facilities will handle latency-sensitive edge processing, real-time application routing, and user interface delivery. Orbit will serve as the heavy compute backend, handling the massive, energy-intensive, and asynchronous AI training workloads that the terrestrial grid can no longer support. This distributed model integrates the reliability of terrestrial networks with the power density of orbit to sustain the scaling requirements of global intelligence.